In the distant reaches of our solar system, where the sun is little more than a bright star in an endless night, Pluto spins quietly, a world that refuses to fade into obscurity. Once hailed as the ninth planet, then demoted to a dwarf planet, in 2006, Pluto has never loosened its grip on our collective imagination. Its story is one of reinvention, a tale of a tiny, icy body that defies expectations and challenges everything we thought we knew about the cosmos. Far from being a frozen relic, Pluto has revealed itself to be a dynamic world, sculpted by geological forces, cloaked in a thin, shifting atmosphere, and possibly hiding a liquid ocean beneath its frosty crust. This is not the Pluto of old astronomy. Textbooks are blurry, at the edge of our reach, but a vibrant, complex world that beckons us to rethink the boundaries of planetary science and the potential for life in the universe's most extreme corners. The journey to this new understanding began in earnest with NASA's New Horizons mission, which, after a 9-year voyage across 3 billion miles, reached Pluto in July 2015. The spacecraft's fleeting flyby delivered a treasure trove of data, unveiling a landscape that stunned scientists and captivated the public. Towering mountains of water ice, some rivaling the Rockies in height, jutted from the surface. Vast plains of frozen nitrogen, smoother than any seen elsewhere in the solar system, stretched across a heart-shaped basin named Sputnik Planitia. Fractured terrains and jagged ridges hinted at a world reshaped by forces far more active than anyone had anticipated. Most surprising were the signs of cryovolcanism, ice volcanoes that may have erupted with slurries of water, ammonia, and methane, suggesting that Pluto's interior is far from dormant. These discoveries shattered the image of Pluto as a cold, dead rock in the Kuiper Belt, a region of icy bodies beyond Neptune, and instead painted it as a geologically lively world, perhaps still evolving today. At the heart of this transformation lies Sputnik Planitia, a gleaming basin that dominates Pluto's surface. Its smooth, crater-free expanse suggests it formed relatively recently, perhaps within the last few 100 million years, a blink in cosmic time. The basin's alignment, almost perfectly opposite Pluto's largest moon, Charon, offers a tantalizing clue about the dwarf planet's inner workings. Scientists propose that Sputnik Planitia's formation triggered a process called true polar wander, where Pluto's crust shifted to reorient the basin in line with Charon's gravitational pull. Such a dramatic realignment would be far more likely if a liquid layer, a subsurface ocean, existed beneath Pluto's icy shell, allowing the crust to slide over it. This idea, once speculative, is now supported by multiple lines of evidence. Computer models show that only a small fraction of scenarios without a liquid ocean can explain Sputnik Planitia's position, making the case for a hidden sea compelling. This subsurface ocean, if it exists, would be a game-changer. Pluto's surface is punishingly cold, averaging minus 375 degrees Fahrenheit, 225 grados bajo cero, where even nitrogen freezes solid. Yet, beneath its icy crust, a reservoir of liquid water could be kept warm by residual heat from radioactive decay in Pluto's core or tidal interactions with Charon. This isn't mere fantasy. Other icy worlds, like Jupiter's moon Europa and Saturn's moon Enceladus, harbor similar oceans, and both are considered prime candidates for life. The possibility that Pluto, so far from the Sun, might share this trait forces us to reconsider what makes a world habitable. Water is a key ingredient for life as we know it, and its presence, even in liquid form beneath miles of ice, raises profound questions about the potential for microbial organisms to survive in such an extreme environment. Adding to the intrigue are signs of cryovolcanism. Unlike Earth's fiery volcanoes, Pluto's cryovolcanoes would erupt with icy mixtures, spewing water, ammonia, and methane onto the surface. Two prominent features, informally named Reitmonks and Picardmonks, stand as evidence. These massive structures, rising thousands of feet, show remarkably few impact craters, suggesting they were active in the geologically recent past, perhaps even within the last few million years. Such activity implies that Pluto's interior remains warm enough to sustain liquid reservoirs, cycling nutrients and energy to the surface. On Earth, volcanic activity near hydrothermal vents supports thriving ecosystems in the deep ocean. Could Pluto's cryovolcanoes create similar niches, where organic molecules and heat provide the conditions for life? The answer is uncertain, but the parallels are striking. Pluto's atmosphere adds another layer of complexity. Thin and ephemeral, it is primarily nitrogen, laced with methane and carbon monoxide. As Pluto follows its 248-year elliptical orbit, swinging closer to the Sun and then retreating to its farthest reaches, its atmosphere undergoes dramatic changes. When nearer the Sun, surface ice is sublime, turning directly into gas and thickening the atmosphere. As Pluto moves away, these gases freeze and collapse back onto the surface, creating a cycle of seasonal transformation unlike anything seen on Earth. Observations from the James Webb Space Telescope in 2025 revealed layers of haze extending over 200 kilometers above Pluto's surface, formed when ultraviolet sunlight breaks down methane into complex hydrocarbon particles. These particles, called thorylins, give Pluto's atmosphere a faint blue tinge and settle onto the surface, staining it a reddish hue. Pholanes are more than just a cosmetic feature. They are organic compounds, potential precursors to the chemical building blocks of life. Their presence on Pluto, also found on Enceladus and Europa, fuels speculation about the dwarf planet's role in prebiotic chemistry. The relationship between Pluto and Charon further deepens the mystery. Charon, nearly half Pluto's size, is so large relative to its parent that the two form a binary-like system, orbiting a common center of mass outside Pluto itself. They are tidally locked, always showing the same face to each other, a gravitational dance that may generate enough internal flexing to sustain Pluto's subsurface ocean. Charon itself is no mere sidekick. New Horizons revealed a world of massive canyons, smooth plains, and possible ancient cryovolcanic flows, hinting at its own complex history. This dynamic duo offers a unique laboratory for studying how icy bodies evolve in the Kuiper Belt, a region filled with primordial remnants of the solar system's formation. Pluto's significance extends beyond its own mysteries. As one of the largest known Kuiper Belt objects, it serves as a window into the early solar system. The Kuiper Belt, a vast ring of icy debris beyond Neptune, holds clues about how the planets formed and migrated to their current positions billions of years ago. Pluto's composition, rocky core, icy mantle, and organic-rich surface mirrors the building blocks of the solar nebula, offering insights into the processes that shaped Earth and its neighbors. Recent discoveries, like the 2025 identification of a new dwarf planet candidate, 20170F2001, with an orbit stretching 151 billion miles from the Sun, suggest the Kuiper Belt may be far larger and more diverse than previously thought. Studying Pluto helps us piece together this cosmic puzzle, revealing how volatile compounds like water and organics were delivered to the inner planets, potentially seeding life. The New Horizons mission, though a triumph, left many questions unanswered. Its high-speed flyby captured only one side of Pluto in detail, leaving the far side a tantalizing mystery glimpsed in low resolution. Future missions, perhaps an orbiter circling Pluto for years, could map its entire surface, monitor its seasonal, atmospheric shifts, and probe for that elusive subsurface ocean with radar. Such a mission would face daunting challenges: communication delays of up to 10 hours, extreme cold, and the need for long-term reliability, but the rewards could be transformative. An orbiter could measure heat flow from Pluto's interior, analyze its atmospheric chemistry over time, and confirm whether liquid water truly lies beneath the ice. These answers would not only deepen our understanding of Pluto but also refine our models of habitability across the cosmos. The public's fascination with Pluto owes much to its underdog story. Its 2006 reclassification sparked heated debate, with schoolchildren sending letters of protest and scientists grappling with the definition of a planet. Figures like Neil deGrasse Tyson, who advocated for the IAU's decision, became lightning rods for this controversy. Tyson, in his book The Pluto Files, chronicled the emotional outpouring, from hate mail to heartfelt pleas to restore Pluto's planetary status. Yet, this demotion freed Pluto from rigid expectations, allowing scientists to appreciate it as a unique world among many in the Kuiper Belt. Tyson's role as a communicator has kept Pluto in the spotlight, emphasizing that its scientific value transcends labels. While no specific big reveal from Tyson emerged in 2025, his ongoing lectures continue to frame Pluto as a symbol of cosmic discovery, urging us to embrace the unknown. Pluto's story is also a testament to the power of exploration. Before New Horizons, it was a faint smudge in even the most powerful telescopes, a symbol of the solar system's frontier. In just a few hours, the spacecraft transformed it into a world of vivid detail, with icy mountains, nitrogen plains, and a heart-shaped scar that captured hearts worldwide. This leap from mystery to clarity underscores the importance of direct observation. The Kuiper Belt, with thousands of objects, like Pluto, holds countless untold stories. Each mission to these distant worlds peels back layers of the solar system's history, revealing how planets formed, how water reached Earth, and how life might emerge in unexpected places. The technological feats behind New Horizons inspire. OU launched in 2006. It traveled over 3 billion miles, using gravity assists from Jupiter to slingshots toward Pluto with pinpoint accuracy. Its instruments, powered by a small nuclear generator, operated flawlessly in the deep cold of space, capturing data that will fuel research for decades. This patient, ambitious endeavor stands in contrast to the instant gratification of modern life, reminding us that the most profound discoveries require years of planning and a willingness to embrace uncertainty. The mission's success has sparked calls for a return to Pluto, perhaps with an orbiter or even a lander to sample its icy surface and probe its depths. Pluto's reclassification, far from diminishing its importance, has elevated it as a symbol of scientific evolution. The debate over its status forced astronomers to refine their definitions, paving the way for new discoveries about dwarf planets and exoplanets. It highlighted the diversity of worlds in our solar system, from rocky terrestrials like Earth to gas giants like Jupiter to icy bodies like Pluto. This shift in perspective has broadened our understanding of what constitutes a planet, encouraging us to study each world on its own terms rather than forcing it into outdated categories. Emotional resonance of Pluto's story cannot be overstated. Its demotion tugged at heartstrings, sparking a global conversation about our connection to the cosmos. For many, Pluto was more than a celestial body. It was a symbol of the familiar, a distant outpost that felt oddly personal. Its heart-shaped basin, revealed in stunning detail, only deepened this bond. Scientists, too, feel this pull. The data from New Horizons, meticulously analyzed over years, continues to yield surprises, from the discovery of tholins to the possibility of recent geological activity. Each finding chips away at our assumptions, reminding us that the universe is far stranger and more wondrous than we can imagine. Looking ahead, Pluto's role in planetary science is far from over. The Kuiper Belt, with its thousands of icy objects, remains largely unexplored. Missions like New Horizons, which studied the Kuiper Belt object Arrokoth in 2019 and measured cosmic background light in 2025, show that this region is a treasure trove of data. A future Pluto orbiter could reveal seasonal changes in real time, map uncharted regions, and test theories about its internal structure. Such a mission would build on the legacy of Voyager, Galileo, and Cassini, which transformed our view of the outer planets and their moons. What challenges are immense, powering a spacecraft for decades, navigating vast distances, and enduring temperatures near absolute zero. But humanity has proven capable of overcoming such hurdles. Pluto also invites us to reflect on the broader implications of exploration. Every mission to the outer solar system pushes the boundaries of what we believe is possible. The discovery of organic molecules on Pluto, similar to those on Enceladus and Europa, raises questions about the prevalence of life's building blocks across the cosmos. If a world as distant and cold as Pluto can harbor such chemistry, what might we find on exoplanets orbiting other stars? The search for life, once confined to Mars and a few moons, now extends to the solar system's fringes, challenging us to redefine habitability. The interplay between Pluto and Charon offers a microcosm of this complexity. Their gravitational dance, with Charon's massive canyons and Pluto's cryovolcanoes, suggests a system in constant flux. This dynamic relationship mirrors the broader solar system, where planets, moons, and smaller bodies interact in ways that shape their evolution. Studying Pluto and Charon together provides a model for understanding binary systems elsewhere. From asteroids to distant exoplanets, Pluto's reddish hue, born from tholins, evokes a sense of alien beauty. These organic compounds, formed high in the atmosphere and settling onto the surface, hint at processes that may have occurred on early Earth. The presence of tholins on other worlds suggests a universal chemistry, one that could bridge the gap between inanimate matter and the first sparks of life. While Pluto's extreme environment makes microbial life unlikely, the discovery of extremophiles on Earth in boiling vents, acidic pools, and frozen lakes shows that life can thrive in conditions once thought impossible. If Pluto's subsurface ocean exists, warmed by internal heat and enriched with organics, it could harbor niches where simple organisms persist, unseen for billions of years. The Kuiper Belt itself is a frontier of discovery. Objects like 2017 OF-201, identified in 2025, hint at a region far larger and more diverse than previously imagined. These bodies, frozen in time since the solar system's birth, preserve the raw materials of planet formation. By studying them, we learn not only about our own origins but also about the countless systems beyond our Sun. Pluto, as the largest known Kuiper Belt object, serves as a guide, its surface a canvas of cosmic history. The call for future missions grows louder with each new finding. An orbiter circling Pluto could monitor its atmosphere as it waxes and wanes, measure heat flow to confirm internal activity, and use radar to peer beneath the ice. Such a mission would require innovations in propulsion, power, and communication, pushing technology to new limits. Yet, the precedent set by New Horizons shows that such feats are within reach. The spacecraft's success was a triumph of human ingenuity, from its precise trajectory to its ability to operate in the deep cold of space. A new mission could carry instruments to detect organic molecules in greater detail, perhaps even sampling cryovolcanic deposits for signs of prebiotic chemistry. Pluto's story resonates because it mirrors our own quest for understanding. Its reclassification was not a demotion but a liberation, allowing us to see it as part of a broader tapestry of worlds. The debate over its status sparked a global conversation, reminding us that science is not static but a living process, shaped by new data and perspectives. Figures like Neil deGrasse Tyson have amplified this message, framing Pluto as a symbol of curiosity and resilience. His work, from lectures to books, underscores that exploration is about embracing surprises, not clinging to outdated truths. In the end, Pluto is more than a dwarf planet. It is a beacon of the unknown, a reminder that even the smallest worlds can hold profound secrets. Its icy mountains, nitrogen plains, and possible ocean challenge our assumptions about where life might exist and how planets evolve. As we gaze toward the Kuiper Belt and beyond, Pluto urges us to keep exploring, to send spacecraft into the void, and to ask questions that push the boundaries of what we believe is possible. Its story is unfinished, a chapter in the larger saga of human discovery, waiting for the next mission to reveal what lies hidden in its icy heart.